Well, the next example is also one that you may have worked in earlier classes together. Really relatively simple. Let's first of all just state the problem. This was pretty much the way it was given, in that there was a figure with it. A slide 2 inches tall is located 10.5 feet from a screen. What is the focal length of a lens that will project an image 40 inches tall on the screen? Where must the lens be placed? And it was given, you were given this figure here. There's the 2 inch tall object, a lens. It is a converging lens, and it casts an inverted image that's 40 inches tall at a distance of 10.5 feet from the slide. So this is sort of an old slide projector, 35 millimeter slide projector. And so again, this is an imaging problem. And so for imaging, getting images of objects, put the input plane on the object and put the output plane on the image. I know this total distance is 10.5 feet. And given some of these dimensions in inches and some in feet, so this is obviously an engineering type problem. But I know that 1 foot is 12 inches, and so 10.5 feet is 126 inches. The point is you need to convert all of these either to feet or to inches, or if you want centimeters or meters. But I converted to inches. That seemed to be the easiest thing, or what they wanted you to do here. So if this total distance from the slide to the screen is 126 inches, which is 10.5 feet, then the distance, the rest of this distance, and well, I don't know how far to place the slide from the lens, but I'll just call that x, as I don't know it. And then the rest of this 126 inches has to be 126 minus x, so that the sum of these two add up to be the 10.5 feet. And as usual, once we've got our input plane and object plane, we go from left to right, and we write it from right to left. So I first have to get from the object to the front of the thin lens, and that's simply a translation, and that's through a distance x, and the translation matrix is 1x 0, 1. And then I need to go through the lens. It's a thin lens, so that's effectively going just from one side to the other all at the same point. And that transformation for the thin lens, if you look in your table, in your textbook, that's 1, 0 minus 1 over f t, or 1. And then finally, we do the last one, which is a translation through 126 inches minus x. And so there is our distance d, and another translation matrix. And then I multiplied these out. 1 is the first one, is pretty easy. The second one simply becomes minus 1 over f, and then the only one of substance really is this last one, which is I'll get 1 times 1 minus x over f, and that's this one here. And then finally multiply out the last piece, so I'll get 1 minus 126x over f, and on this one I'll get x plus 126 minus x times 1 minus x over f. And then the second row, this one just reproduces that second row, since there's a 0 in the first column. And now then we take our imaging conditions. We know that imaging condition is setting b equal to 0. But let's look at a few other things. Oh, and then when b is equal to 0, well, the a is equal to the lateral magnification. And I can actually get that here, hi over ho, because I know the image is inverted, so it's minus 40 inches, and we're given it was 40 inches tall. and the object was 2 inches. And so when I divide this out, I get minus 20 for A, and that's the magnification. But now let's do something that sometimes is helpful, and you should always keep this in mind, and that is this condition here, that the determinant of M, the matrix, is always the index of refraction, the final of where you are finally to where you were initially. Well, in our system, we're in air over here and we're in air over here, and so both NF and NI are 1, and so this determinant of the transformation matrix has got to be equal to 1, and sometimes it's useful to use that condition. It's just AD minus BC is the determinant of a 2 by 2 matrix, and that's equal to 1. But remember, we're at an imaging, we're at the image, so we have an image condition. At the image plane, B is equal to 0, so this one goes out, and I get that A times D is equal to 1. But as we've seen, A is minus 20, and so D is minus 1 over 20. And now then finally I can use our full imaging condition. Here is A, here's B, here's C, here's D. Okay, so here's B. I set that equal to 0. That's just here. But I notice also that this D, 1 minus XF, is also right here, and this value I have. I've got D. D was equal to minus 1 over 20, so I can use that. I substitute for this value, which is the same as D, the minus 1 over 20. And that simplifies the algebra quite a bit, actually. So multiplying this out, I get minus 1 over 20 times 126 is minus 126 over 20. Minus and minus is a plus, so I get x over 20 here. I can combine the x and 1 over 20, and that gives me 21 20ths times x, and then take this over to the other side. And then finally divide through by the 21 over 20, or multiply through by 20 over 21. And I get 120, the 20s cancel the 126 over 21. And when I divide that, I get 6. And since I was consistently, everything is in inches, this is in inches, so x is 6 inches. To find the focal length, I can go back to our D expression. That was 1 minus x over f, but I know D is minus 1 over 20. And that gives me, I now know x is 6 inches, so that gives me all the information I need here to determine what the focal length of the lens needs to be. So I solve this equation for f, and when I do that, I get a positive 5.71 inches. Well, I'm not really used to working in inches here, but one has the final solution. The focal length of the lens needs to be, this needs to be a lens with focal length 5.7 inches, and this distance x that this needs to be in front of that lens is 6 inches. So that gives you some alternate things. Sometimes these you can use these to get to good advantage that the determinant of any transformation optical transfer matrix has to be the final index of refraction over the initial, and then that oftentimes, particularly in cases where you're looking at imaging, that reduces to this set here. And it can often be used to simplify some of the algebra. That's not essential. You can always solve 2 equations and 2 unknowns, but take my word for it, it gets messy, and the easier way to go is usually to use this determinant condition that one has. has also on the optical transfer matrix.